Hello and welcome to another United Learning Required Practical video. Today we're looking at specific heat capacity. As we know, when we add energy to a material, we increase that material's thermal energy store, and we detect that by a change in temperature. However, different materials will require different amounts of energy in order to increase their temperature by 1 degree Celsius. And a material that requires a lot of energy to increase its temperature by 1 degree C, we say that has a high specific heat capacity. Today we're going to be looking at how we can measure the specific heat capacity of a particular material. We can transfer energy to a material using an electric heater. The energy goes from the heater, when switched on, through the wires and to this thin cylinder, which I can use to heat any material. You can see the metal block has two holes in the top, one for the cylinder and a second hole for the thermometer to record temperature. And the equation linking all of these variables is that the energy change is equal to the specific heat capacity times by the mass and times by the change in temperature. To find the specific heat capacity, we simply need to rearrange this equation. And you can see we also need to know the mass. Now, we have 1 kilogram blocks here, these are given, but if you didn't know the mass, you'd simply need to use the top-to-pan balance. Notice that we're trying to find the change in temperature, delta theta, and so we need to find our temperature reading at the beginning and also at the end. When we have our two values, we'll just subtract one from the other to find our difference. Measuring the energy transferred is a little bit trickier, but if I know what my heater's power rating is, I can just use the equation energy is equal to power times time in order to find that. If I can't find what the power rating is for my heater, then I can use an ammeter and a voltmeter, connect these up, and I'll be able to find my power rating by doing power is equal to current times voltage. Here you can see one series circuit with the ammeter and the heater, and finally a voltmeter in parallel. So as I've said, the smaller hole here is for the thermometer. However, the thermometer is surrounded by air. We can see here this would have very poor thermal contact. Air is a very bad thermal conductor. It's not very good at conducting the heat, and we of course want the thermometer to be at the same temperature as the metal block. In order to fix this problem, I'm going to fill the hole that the thermometer is in with water, and this will guarantee what we call good thermal contact. Now when I add the thermometer to the hole, you can see it is filled with water. So, now that we've calculated the power and we know the amount of energy transferred to the cylinder per second, I've got the cylinder in the block and the thermometer surrounded by water to give it that good thermal contact. Now I can turn on my power supply and start my timer at the exact same time. All I need to do now is wait for a given time, say 5 minutes, and I'll record the final temperature at the end. Recording the initial temperature as 22 degrees, I now need to wait for this 300 seconds. While I'm waiting, we can think about some ways we can make this experiment that little bit better. One way might be to record values every 30 seconds, plotting those on a graph, and finding a line of best fit to go through them. It's also very important that we make sure we don't touch this metal block, particularly towards the end of the time, as the temperature will have increased dramatically and it will be very hot. So I've now recorded my final temperature, I've put that into my table, and I can use that to calculate the temperature difference. Taking that value, taking the 1 kilogram mass and the energy change over 300 seconds that I calculated earlier, we get the following results. And there you have it. I've calculated the specific heat capacity for this material, aluminium. However, if we look at the true value of aluminium, you'll see that our value is somewhat higher. What might be the reason for this? Well, there are a few reasons. One, it would have been more reliable, more accurate to plot the measurements every 30 seconds and find a line of best fit for our results. But also you can see that like most energy transfers, this is not a 100% efficient transfer. Looking at the block here, you can see that the cylinder is not completely within the metal block. Therefore, some of the heat from the cylinder is radiating outwards straight into the air. Another reason, of course, is that the metal block is also radiating heat out into the air. And therefore, one way that we might make this more accurate is to wrap the whole thing in insulation, keeping all of the energy transferred to the block inside the block, or as much as possible. Following this procedure with other metal blocks, I could compare different metals and see which requires the most energy in order for the temperature to be increased.